Alright, in this video, I will be reviewing the topic of vertical asymptotes in terms of, in the context of calculus, and also how you would find these, identify or locate these vertical asymptotes algebraically, even without using your graphing utility. So here's the definition of the vertical asymptotes in our context. The line x equals a is a vertical line, is a vertical asymptote of the graph of the function y equals f of x if either the limit of f of x approaches positive or negative infinity as x is approaching a from the right side, or from the left side, that's fine too. So as an illustration, take a look at the vertical asymptote here. At pi over 2, we see that the limits of the function tangent of x as x is approaching pi over 2 from the right side is equal to, from the right side, I want you to see the trend, see the pattern. Okay, from the right side, if you're getting closer and closer to pi over 2, and your answer appears to be negative infinity. Okay, however, if you're approaching the x value for the tangent from the left side, then your answer appears to be positive infinity. In either case, you're satisfying one of the conditions, okay, for you to have the vertical asymptote. Take a look at the second graph right here. So we have the graph of y equals 1 over x squared. As you can see, in either case, okay, from the left side, from the right side, as your x value of the function is approaching 0, the y value is just constantly increasing. So we could say that the limit as x approaches 0 from either side of this function, 1 over x squared in this case, let me actually write 1 over x squared is equal to positive infinity. Okay, this time your left limits agreed with the right limit. So you could combine those two statements. Algebraically speaking, okay, how do you find your vertical asymptotes? I'll give you a simple example. Okay, let's go to 1 over x squared again. Okay, so think about 1 over x squared. Okay, think about what x value would make that whole function undefined. What is the x value that's going to make the whole function undefined? Your x value would have to be 0. When x equals 0, this whole thing will be undefined, regardless of what the y value is. Okay? Take a look at the function g of x here. What x values would make this whole function undefined? Okay, you got it. X cannot be. So your vertical asymptotes would be x equals 1 and x equals negative 1. These two vertical lines, because the function itself will never reach those x values. And it would satisfy your definition of the vertical asymptotes in terms of limit. If you look at another expression here, f of x equals x squared minus 3x plus 2. Okay, I guess I don't need the parentheses on the denominator. Notice that the degree of the numerator is greater than the degree of the bottom. And notice that you could also simplify this more by factoring. So what happens is that though x cannot be 1, this whole function f of x behaves like a line. Okay, basically a linear equation, x minus 2, even though you started with a linear function. Okay, so the moral of the story is that any rational function that has a higher degree on the numerator as opposed to its denominator will not have a vertical asymptote. Okay, we're gonna talk about vertical asymptotes if the degree on the bottom is higher than the degree on the top. Okay, so let's take a look at one more example here. Also, getting back to that point, okay, so though x cannot be 1, so what is that then? If it's not a vertical asymptote, then that's just a void, okay, on the graph, okay, or you could call it a hole on the graph. When x equals 1, your y value, your function is not defined. It leaves a little void, okay. That's again, what is that? How do you represent that on the graph? You could leave an open circle at x equals 1. For my third example, so once again, you're able to factor out the numerator. And notice you can cancel out one of the factors on the bottom. Okay, what that tells me is that at negative 3, when x equals negative 3, though x cannot be negative 3, that's not a vertical asymptote. So that's a hole. So essentially, your graph is behaving like behaving as if it was x plus 1 over x plus 11 times x. So your vertical asymptotes are these then. Okay, so as for your vertical asymptotes, it has to do with x plus 11 and x on the denominator. Okay, the values that x cannot be are negative 11 and 0. So these are your vertical asymptotes. But again, x equals negative 3, that's just a hole, not a vertical asymptote. So here's a graph of that. As you can see, when x equals 0, you have a vertical asymptote. When x equals negative 11, you have a vertical asymptote. But when x equals negative 3, let's see. So negative 3, we just passed it. I think we just saw it. Yeah, negative 3. It leaves a little hole on the graph itself. So that's our little review of the vertical asymptote.